Hello class, and thank you for watching the first part on section 3.4, composition of functions. In this section, we're going to go over how to create a new function by using function operations. Now, the algebra of a function dictates that if we're given two functions or more, the sum, difference, product, and quotient of these two or more functions, whose domain is the set of real numbers, common to the domain of each function, is defined by the following. So the sum means that we're going to add two functions together, and the notation will look like this, where f plus g of x means that we have this function f of x, and we're going to add it with the function g of x. And then we have our difference one, where f minus g of x just simply means that we're subtracting those set two functions. And then we have our multiplication and our division. Again, simply dividing those two set functions. Now there is, just in case again, just in case you're not clear, there is a different way of writing multiplication, that instead of using the dot, we can just simply write fg of x. But again, that's the concept behind multiplying f of x times g of x. So we don't necessarily have to put that dot in between. We can just write it like that. And the same thing right here, we don't have to write this dot. We can just write f of x, g of x next to each other, which looks kind of weird. So most books and most places, most reading material do put a little dot in between to indicate that we're multiplying these two functions. So let's look at some examples of this, and we'll start with sum and difference, and how do I add two functions together. So in this first example, I have here that f is 3x minus 5 minus 1, and g is x squared plus x minus 2. So let's write those two functions. So we have, and we want to add them. In the first example, we want to add those two functions. So this notation again simply means that I have this function in terms of x, and I'm going to add it with this other function in terms of x. So we get 3x to the second power minus 5x minus 1, my f function. I'll add it with my g function as such. I like to put parentheses around it, especially on these occasions, so we understand that again this is f, this is g, and we're adding those two things together. From here, we're just simply going to require the skill to add these is to combine like terms. So if I highlight the corresponding like terms, like x squared corresponds to x, 1x squared, negative 5x corresponds to the positive 1x, and the constant of negative 1 corresponds to the constant of negative 2. We're simply going to combine those like terms together. So we're going to get the following. And there, this is our sum. This is the sum of these two functions. Now, if we're going to subtract them, I'm going to set it up the same way. And now simply subtract those quantities. Now, what I told my students normally when it comes to subtraction, yes, you can just do it 3 minus positive 1, negative 5 minus another positive 1, and negative 2 minus a negative 2. And if you can handle that and do that in your head, you're more than welcome to do that. But for those students that make mistakes again with subtraction, my recommendation is to distribute this negative sign into this second parentheses. So we end up dropping the parentheses on both of them. The first one doesn't change because technically there's this assumed invisible 1 there, and distributing that doesn't change anything. But on the second one, distributing this negative or this negative 1 into the second parentheses is going to change the signs here. So we end up with negative 1x squared, negative 1x, and a positive 2. And then you can then use the same technique that we did in the previous one and combine like terms from left to right. So let me highlight the corresponding like terms, and then we're going to do the operations from left to right. Hold on, I'm missing a term right here. Negative 1, and now negative 1x squared minus 1x and plus 2. There we go. let me just finish highlighting. There we go. And now we can combine our like terms. So our like terms are going to be, again, the red ones and the yellow ones, and from left to right, this is 3. Ignore all of this. Minus 1. So 3 minus 1, that's 2. So 2x squared. Negative 5 minus 1, negative 6. And negative 1, again, ignore all of this and go to here. So from left to right, we have negative 1, and we're adding positive 2. So negative 1 plus 2, that's positive 1. So there is the difference of f and g. Now let's look at example 2. In example 2, we have two different functions, but this time we want to multiply our two functions. So we have 8x minus 9, so f is 8x minus 9, and g is 2 minus 3x. As indicated, this notation means to get this function in terms of x, and this function g in terms of x, and multiply them together. So I'm going to use parentheses to group them. This is f, this is g, and we're simply going to multiply. And this again requires just distribution or FOIL. Multiplying the first term with the first term, which is a total of 16x, multiplying the outer terms, the outer terms, which is negative 24x to the second power, multiplying the inner terms, negative 18, and then multiplying the last terms on each function. So negative 9 and negative 3, that's a total of positive 27x. And again, from this point on, we just simply combine our set of like terms, which in this situation, we only have one set. The linear terms of 16x and 27x. So I'm going to bring everything down first. I'm going to write this in degree and the order of the degrees. So 24x to the second power goes first. Our linear term will go second, so that will combine 16 and 27, which is a total of 43. And we bring down the minus 18. So here is the product of f and g. So just requires, again, distribution. Now, if we look at the last example, or the next example of example 2, 2D, here we want to get the ratio. This notation means that I simply want the ratio of f of x over g of x. We're not going to actually do any division, at least not today. So here, f is 8x minus 9, and g is 2 minus 3x. So that would be your answer for these type of problems here. Now, because these are straightforward, when you write in the ratio, I do want you to identify the domain of these particular ones. The domain of the other functions are all real numbers. There's no restrictions, but because this creates, again, a rational function, I am interested in finding the domain for this. So how do we do that? Well, we simply look at our denominator of our ratio, so 2 minus 3x, and set it equal to 0. And in this particular example, we have a linear equation. So that simply requires our technique of linear algebra, inverse operations, which I know some of y'all are familiar with, letters to the left, numbers to the right, that kind of scenario. And that's exactly what we're going to do. So here we're going to start by subtracting 2 from both sides, because that is my constant. So we remove the constants. We're going to divide by negative 3. And we find that x equals to positive 2 over 3. So since this is the number that, again, makes the denominator equal to 0, this number gets excluded from the domain. So we're going to say that our x cannot equal to 2 over 3. So like a toxic person, again, in your life, this number is toxic to this function. It makes this function, again, not work and not have a value. So its domain cannot exist at. So this number is not allowed within the domain, within the boundary of what numbers x has allowed. And again, just like in real life, this any toxic situation, they're not allowed in your personal domain. So that's exactly what we're doing to this function. We're letting x be any number except for that one there. So that would be the domain for this example here. Let's now look on the next page, the composition of functions. The composition of functions is just I want to say operation, but it's another way of creating a new function using two or more functions, okay? Now the notation for this, again, operation, for lack of a better word, is this symbol right here, okay? So it's a very unique and distinct symbol from just like plus, minus, times, and dividing. And what this operation does, again, you can't see it, but I'm using air quotations, is that it plugs in the function to the right of this symbol into the function on the left. So it does this. This is the notation for that idea. So we're going to substitute in the rule for g, because it's on the right, into the input values to the function that is on the left of that notation, okay? And this is referred to as the composition of functions. Now I have a little diagram to represent this idea, which again, you can just simply look at your notes. So let's look at the examples of how we actually use this, okay? So here I have my function f and g, and we want to find the corresponding compositions for example 3. And we want to go in this order, okay? F of g of x is the way that we read this. F of g of x. And this notation means, let me change the thickness of the pen. That we're going to plug in the rule of g into the x of f. So I'm going to write f first and g second. And what we're doing, like I said, is because of the order that we have this, we're going to get this function g, which is 3 minus x, and plug it in to the x of the function on the left, which is f. So we're going to plug it into that value. So fog, or f of g of x, I like calling it fog because it looks like the word fog. Fog of x will equal to 3 times the value of x minus 4. And like I mentioned, we're going to replace the x where my parentheses are with g. So 3 minus x. And there. Technically, this is your answer because, again, we have the composition. It's simply about doing that. Now, to simplify it, however, because we're doing this, I do want you to practice your algebra. So I do want you to simplify this, which will distribute the 3 into the parentheses, giving us the following. And then combining like terms, which is the combining of the 9 and the 4, that's going to give us 5 minus 3x. So in simplified form, fog of x equals to this. Let's see, let's try the next one. Let's do another example. So here we have the same, we're going to use the same two functions, but now we want to do the composition in this order, which means that we want now to plug in f into the function g. So I'm going to write g first, which is 3 minus x, and f second, which was, I forgot, 3x minus 4. So now we want to do the following. We want to get this and plug it into this x right there. So the golf, as I lovingly call this one because it looks like the word golf, just without the L, golf of x equals to 3 minus 1x. So I'm going to write 3 minus 1x. So I write this function and put parentheses where the x is. And since there's an invisible one right there, I'm going to put that there. And inside the parentheses, I'm going to write an f. And now we simplify by using distribution first, and then combining like terms. Now let me give you a little warning. Again, I've seen this error occur multiple times. Some students have a tendency of subtracting these two things first because they read this from left to right. But remember, this again is subtraction while this is multiplication. And according to PEMDAS, multiplication takes priority before, again, subtraction. So the distribution is required to be done first, and then we can combine the like terms. And here from left to right, we would only be able to add the 3 with this 4 at the end. So ignoring the middle one, so let me just write negative 3x first. Let me bring that down. And if I ignore that and just read this as 3 plus 4, that gives us a total of 7. So there is your composition. Okay, so let's now look at the next example, example 4, part A. So just again, the notation is a little bit different. I rewrote it as f of g of x, which again is just fog. So we have the fog of x, which means we want the function on the right to be plugged into the function on the left. So I'm going to write f first on the left side. I'm going to write g second on the right side. And we're going to go from right to left. So I'm going to plug all of this into this x right here. So the fog of x will equal to 4 minus 2 times the value of x. And we're going to replace that again with x squared plus 3. Now to simplify this is going to require us to distribute. So we have 4 minus 2x squared minus 6. And now combining like terms from left to right, we would get negative 4 and subtract 6 from it, which is negative 2. So negative 2 minus 2x squared. And there is your composition. Let's now look at the last example. Let's use the same two functions, but now let's write it backwards. So now we want to do the golf. This notation means we're going to do the composition in this order. So the function on the right, f, gets plugged into g. So I'm going to put them in that order. So I'm going to write g of x equals x squared plus 3, and f of x equals, what was it, 4 minus 2x. So 4 minus 2x, okay? And again, the composition simply just requires us to do the distribution, to do the substitution, and see what we end up with. And I like to write it again like this in the notation that I have up there. You don't have to always write it in that. If you want to keep f and g always in the same order, as long as you understand in the direction that you're substituting it. I always do it like this, so I just keep it consistent, always plugging in the one from the right into the one to the left. And that's, again, the order that's given up there. But if you want to write it again, f here and g there, it'll be the same thing. You're just going from this to that, and the order doesn't really matter. Okay, so as long as you know what order to follow up there, the order down here doesn't matter. So let's now plug this in, okay? So I'm now going to plug this into that x right there. So the golf of x equals to 1x squared. So 1x to the second power plus 3. And again, this is where the x was. And we're going to replace that again with this right here in blue. So 4 minus 2x. Now, to do this, I cannot distribute whatever this number is inside here first, okay? Remember, exponents take priority. So having this exponent of 2 means I have 2 of these identical things. So I'm going to expand this out, and I have 1 times 4 minus 2x times another 4 minus 2x plus 3. Now, I'm multiplying these three things, and because it's multiplication, the order doesn't matter. I can multiply these two first and then multiply that answer with this, or I can multiply these two values first and then multiply that answer with that. Since the number we're going to eventually end up multiplying, whether it's the first time or the second one, is the number 1, multiplying by 1 doesn't change anything. So I could basically ignore that and pretend like it's not even there because we're multiplying by 1. So I can now focus on multiplying these two things, which just requires, just like on the previous page, multiplying by simply doing the FOIL method. So we're going to multiply, sorry, I'm repeating myself here, positive 4 with 4, so that's going to be 16, 4 with -2, -8x, -2 and 4, that's going to be another -8x, and -2 times -2, that's positive 4, and since they both have x times x is x to the second power. We're going to bring down the 3 because we haven't used that one yet, and now we can combine our like terms. So we have 16 plus 3, that's equal to 19, so let me write 19. -8x and -8x, that gives us -16x. Those are like terms. And the only last term that doesn't combine with anything is 4x squared. And I like my colors, so let me highlight stuff. We have 16 and 3. That's how we got 19. These two terms are like terms. That's how we ended up with -16. And then, of course, the purple number didn't combine with anything, so I just simply brought that down. So this right here is your solution. This is, again, the simplified form of this composition up there. Okay, so this concludes the first part of this lesson. The next part we'll talk about how to evaluate these type of composition functions. We're going to only focus on composition functions and how to evaluate composition functions. Okay, well, thank you for watching, and like always, I hope you have a great day. Goodbye.